Okay. So I hope you remember next week we will have a test exam. So the lecture today is going to be a review with a lot of exercises that I believe it's kind of important for you to know for next week. Um, Also, Ian brought to my attention that only one person submitted the exercise sheet this till now. Okay, good. If you want more time, maybe we can. What happened? You need more time, or it's like you just don't want to do this one? That's fine as well. I mean, I think it's an important one because it's very applied. So it's a chance of you actually seeing things in like a hands-on application of the method. You're huh? The current sheet. So
A different, so this week was really bad for me.
okay.
A different class decided that since we're doing so well in the exercise sheet, they're going to double it. So I had double exercise sheet and then another project that
Okay.
do this week as well.
Yeah, so it's up to you. Since we have the test exam, we won't have exercise sheet this week. So I could actually give you another week. Okay. Don't forget that I actually submit the code in R. So if you want to use my code, it's totally okay. You don't need to code your own thing. Of course, you could code it, but if you prefer Python, I think one person wrote everything Python. It's really nice. But the one that I submitted is in R, so it's up to you. You can use whatever. But it's important for you to see in practice how things work. So I'm giving you this week if you want. Okay, good. So let's start here. So the first idea, I will try to cover just a little bit about the concepts before showing the exercises, but it's going to be very practical. So I'm going directly to the exercises in most of the cases. But implied condition dependency is something that you should know how to read from a causal diagram, right? So a causal diagram, for example, this one, encodes not only the ancestor relationship, so this is a structure of an underlying causal model, but one thing that you can extract from it through this separation is a set of condition dependencies. So we call it implied condition dependencies. And for example, I would like to ask you the set of all condition dependencies implied by this graph. So the first thing that you should look at is the missing edge, because it's the missing edge. Every pair of non-adjacent variables is separated by some set, so this implies some independence. So just look at the missing edge, and of course that is the minimal independencies, which means that they are in condition dependencies given the smallest conditioning set that you can find. So those are called minimal condition dependence, but they're like the entire set of condition dependencies. So let's start, for example, with the V1, V3. So V1 is independent of V3 given the empty set. What do you think? It's
No.
I want no.
Because V2 is on a correct path.
Exactly. So that is like V1, V2, V3 is an open path. So can anyone here just tell me which set would make V1 and V3 separate? Yeah, let's go one by one. So this is not, right? So what about V2? Just V2. No, why not?
So V2, since it's part, it's a collider in that path. So since it's part of the set, it opens that path, and so you have to block the path either using V4 or V5. The problem with V4 is that it's also a collider. If you take a different path, so it has to be V5.
So
right.
exactly.
So it can't be part of it.
So how many paths are open when you condition on V2? When you condition on V2, which path between V1 and V3 is open when you condition on V2?
V1, V2.
Maybe.
And then it depends on V4, V5, V3. That's a path, right?
Yeah, so there are three paths between V1 and V3, right? Can you see it? So the first one is this through the bidirected edge, and then the edge here and another bidirected edge. The other one is through this directed edge and the same thing. And the other is this directed path. So after conditioning on V2, we block this path. But what happened with the other two? So there is a collider in V2 for both paths, right? So it's opening, right, when we condition on this.
But since you're not conditioning on V4, that blocks the upper path because that's a collider, but the lower one, the V2, V4 path is open.
So both are actually open because V2 is a descendant of this collider. So when you condition on V2, so you need to pay attention on the descendants of collider. They're really, really tricky. But it wouldn't matter in this case because if you look at this path through this directed edge here is open, you would not consider V2 as a conditioning set that makes V1 and V3 separate. What about V2 and V5? Yeah, that's correct, right? So because both paths that are open when you condition on V2 are now blocked when you condition on this non-collider here, right? So this is sufficient. What about V2 and V4?
No, because you have a problem where it functions as two things. One's a collider in the path and the other way as a non-collider. And so you have to both have it and not have it, and that's impossible.
Yeah, so we are opening this collider here and also this other collider here. So this is a non-collider, it keeps open. So this path would be open. When you condition on V4, you block the second one here because it's a non-collider, but there's still the second path. So I think now maybe it's a good idea to show fusion. I will try to log it in. Sometimes takes a bit to, yeah, but I like Fusion because of this tool. So you would be able to see the paths that are open. So it seems easy, but when you try to do yourself, sometimes you forget about these special cases, right? So if you try, for example, to see, are these two, can you see here perfectly? So that is this V1 and V3. So that is this path analysis, is a deseparation tool. You can put V1 and V3 as the set that you want to separate, and then ask given which set. So if you don't put anything, it's the empty set. And that is this number which shows which path is open. So when you don't condition on V2, that is this path that we discussed that's open. But if you put V2 here, V2, there are two paths that are open. So that is this one that you can see that's open because V2 is a descendant of V4, which is a collider in this path. And that is also, you can go to the second one, which is open because V2 is a collider as well, and this is a non-collider. Non-collider. V4 is a non-collider in this path. So you can see that's not separated. And when you put V2 and V5, for example, you would see that separate. So you can play. You can construct many graphs here. So you can play with this tool until you master, would say, the separation tool. I think it's a good idea to learn the separation. It seems trivial, but when you do an exercise, it's kind of hard sometimes to catch all these colliders and non-colliders. So what about, so this is done. Oh, okay, so I was here. So V2 and V4 doesn't work, but you can start adding more, right? So for example, once I have V2 and V5, I can start adding other stuff. So the only required ones are 2 and 5. So this is considered a minimal separating set. But that is this other separating set that's not minimal and it's still separating V1 and V3.
And we've done it V4 because it's
No, we don't need V4 because you only need one triplet inactive in the entire path. So this triplet, V4, V5, and V3, which is part of two paths, right? There are two paths, and V5 is part of both. So when I condition on V5, I block these two paths together. Right, and I don't need to block another, to make another triplet inactive. I just need one. Right, okay. So now 3 and 4. What do you think about 3 and 4? We need V5. Is the only one that we need? We need V2. V2 and V5, it's sufficient? Yeah, so exactly. So the empty set doesn't work, only V2 doesn't work, V2 and V5 works. So V2 and V5 is the minimal conditioning set. What about V2, V5, and V1? It works as well. So there is a minimal separating set, but of course, if I ask you to list all condition dependencies, you need to consider every other combination of the other variables that doesn't hurt. V2 and V5.
So you can't have V3 because that's a collider on that path.
Right.
And then the problem is V4 because it functions as a collider in one path and as non-collider in the other path. So you want it, you don't want it, so it's impossible. So it's not deseparable by anything.
Perfect. Exactly. So the empty set doesn't work. If I put V4 there, doesn't work as well. So if you remember, that's exactly the definition of inducing path, right? So if we have a collider path, like V4, so there is a path between V2 and V5, that all the variables in the middle are colliders, like the only one is V4, and these colliders are also ancestors of either V2 or V5, or the first or the last. So that's the definition of inducing path. If this exists, then the pair is not separable. So there's no implied separation between these two. V1 and V4.
It's impossible for the same reason.
Are you sure?
I think it's just V5 alone is enough because
V5? So what are the paths between V1 and V4? Yes, yes. So there are several paths between them, right? So,
right.
Yeah. So it looks like it's a inducing path, but it needs one path that's open and one path with a lot of colliders to actually have an inducing path, right? So here this is a collider, here it's a collider. So the empty set, it's blocking already because it's by default it's already blocked. Now the other path is through this thing here. And this path is also blocked because this is a collider.
Okay. But adding V5 would work in this case, right?
Yeah, let's see. What about adding V2?
That would
be.
It's a problem because it's a collider, and if you take it, then the V1, V2, V4 path is well.
Exactly. So that one cannot go. But if we add V3, no, no, no. I'm kidding. Yeah. So it's why? I want to know if you know why.
Because the V1, V2, V3, V5 path, V5, V4 path. So V2 is on that path is a non-collider, but it's not part of the set, so that's open. V3 is a collider, but it's part of the set, so it's open. And then V5 is a non-collider, and it's not part of the set, so it's open. So the entire path is open. So not blocked.
Is the only path open?
I think so, yes. Because V2 isn't part of it, and so it functions as a blocking collider for the other two paths.
He's paying attention. Well, what V3 is of V2?
So
we can go back here. So what will happen with V1 and V4, right? When we condition on V3. So there are three paths open. So the first one is clear, this one. Oh, no, that's the one that you didn't see. So the one that you saw is this one. But that is this. V3 is a descendant of both colliders here. So all these paths are open. So
so my question, so it's, I don't know, it feels like we're being a bit, I don't know, maybe I'm getting the wrong impression, but sometimes because the path we're looking on, V2 doesn't function as a collider, we kind of ignore that it's a collider on that path. So V3, so
no,
I guess
you never ignore, like,
it feels like we did sometimes though.
no, so to see if it's separated or not, one is sufficient, right? So for example, when we decided that the V2 is not a separating set, it's sufficient to find one path that's open. So when I say, okay, that's a collider, obviously it's connecting V1 and V4, so it's not a separating set. I don't need to look on all of them. So when I ask is V3 a separating set, it's the same thing. So you only need to find one, and you found one. This is sufficient to answer if V3 is a separating set or not. But I asked you, I wanted to know if you were seeing or not. But I want to know what paths are open under the set V3. It's not only this path. There are three paths that are open when you condition on V3.
I
not
understand, but I guess, I don't know, in my mind, like sometimes we ignore the fact that the ancestors are collider and sometimes we don't, it feels like. I don't know.
So to detect if the path is open or not, you need just one collider. Sorry, you need to detect if it's separate, if it's blocked. You need one collider that's not part of the conditioning set, or a descendant of it is not part of. It's not or, it's both. Because the two conditions are like this: either, like you activate the collider on the path, either if the collider is in the set or if a descendant of the collider is in the path. So you are activating this collider on the path. So you are looking on one path only, and you want to know if every triplet is activated or not. So you look at the middle variable. And in the middle, suppose that this middle variable is a collider. This collider specifically is going to be activated either if the collider is in the set or if a descendant of the collider is in the set. Of course, to make the path completely open, you need all triplets to be active. So sometimes you ignore the collider if it's already blocked and you are looking for the separation. So what you need is this, like to make the whole path blocked, you need one triplet inactive, but to know if it's open, you need all triplets to be active. It's the opposite. Maybe we can continue, and then I was here, V1 and V5. I guess no, right? I guess V1 and V4 we were here. So V2 doesn't work, V3 doesn't work, V5 works, right? Because V5, let's go back here. V5, it's here. So we need that all paths between V1 and V4 are blocked. So when I condition on V5, I'm not making this triplet here active, not even this, right? Because I'm conditioning on a variable that's not descendant of V2. So it's just a non-collider. I'm not hurting anything here. So I can condition on V5 without opening this collider or any or this entire path here. Okay. What about V1 and V5? So, oops, you saw already, but V1 and V5, it's kind of the same thing, right? So we had this, the V2 is a collider on the path, so the path is just a bit longer, and now the path here is shorter. So with the empty set, these two paths, the one through the bidirected edge, and the one through the directed edge, they are both blocked because this collider is already blocked. And I'm not conditioning on anything, so I'm not activating the collider, and the other path has also a collider, so it's still blocked. Okay, so it works. What about if I condition on V2? So you just need to find one path that's open when I condition on V2, or just make sure that no path is open conditioning on V2. You can pick the first path, which path you want to look first. Let's pick this one here through this bidirected edge. Okay. So what happened when I condition on V2 with this first triplet? The whole path is open? The first triplet is open. What about the second triplet, V5, V4, V2? Pay attention again.
Well, if you only go the other way. If you only go up.
So I'm conditioning on V2. It's a descendant of a collider. It's really tricky to see.
Wait, how is V4 is a descendant of a collider?
V2 is a descendant of the collider V4 in the triplet V2, V4, V5. It's hard. So you need to do very, very, very slow this type of exercises to not make mistakes. That's why I'm going through here very slowly and asking you to pay attention. Like when I condition on V2, looks like I'm opening, I mean, you would find other paths here. So this exercise, maybe it's not the best one. I actually spent a lot of time trying to find a good one. So because, for example, when I condition on V2, you open this collider and this is blocked, so it would be fine. But maybe if I asked, what about V2 and V4? I mean, I didn't put here. What about V2 and V4 in this case, right? So, I mean, you would see as well because there are two colliders, but just V2 opens this path because not only I'm conditioning on the collider in the first triplet, but also I'm activating the second collider because V2 is a descendant of V4. So the two triplets in this path are activated. Okay. So it's just I wanted to that you like it seems easy, this separation, but I can't find examples where if you don't pay attention you are going to make mistakes, and during an exam it's sometimes you are like in a hurry, and I've seen people making mistakes for very silly things. So I want you to just pay attention whenever you have like this type of exercise. And it's important for you to know that conditioning on descendants of colliders opens the collider. Okay. Okay, so the minimum separating set is the student set. Of course, you can add others without hurting here. Like before, right? So before it is still fine here. Before you're opening this collider, but there is these colliders that are still blocked. So the same here. there is these two definitions, right? The separating set, if the separating set is minimal, then you have a set of minimal implied condition independencies. Of course, you have many more. Maybe I should fix this later. There are some mistakes here. But of course, the set of all condition dependencies is larger than the minimal ones. As an exercise, I would like you to use this diagram to show the factorization of the extended parents. I think this is important for you to know, but I won't take time here in the lecture to do this. It's a matter of going through the definition of extended parents and showing that you're using only independencies that are implied by the graph, right? So if I ask you, show that the factorization of the parents is actually valid on this, then it's just a matter of showing that the condition dependencies that are used in the conditioning in the factorization are implied by the graph. Okay. Questions up to this point? No questions. Okay. So maximal ancestor graph is another concept that we saw. Basically, you have a procedure to go from an ADMG or a causal diagram that takes two steps. The first step is every pair of variables that's adjacent is going to be also adjacent in the mag, but also every inducing peg in the ADMG is going to be connected by an edge in the mag. Let me go in this first step in the example. So the same example, I'm going to use the same example over and over again. So this example here, so first of all, we put an edge in every edge, right? That's trivial, first step. But then we have to check the inducing paths. Is there any inducing path in this example? V5 to V2. Everyone sees this? Okay. So we put here an edge. So now we have the skeleton of the mag. And then we have to just follow the ancestralities. So this is a representation that accounts for all latent confounding by not using bidirected edges. So that's the whole idea behind the maximal ancestor graphs. It's a simpler representation of a class of models without using bidirected edges. We only use we only represent ancestrality. So, for example, how is the orientation between V2 and V5? Okay, because there is a directed path between V5 and V2. V5 is an ancestor of V2, and this is going to be the represented here. What about V5 and V3? Exactly. That is a long directed path from V5 to V3. This is going to be directed from V5 to V3. What about V4 and V2? It's a simple edge. We ignore the bidirected edge. There is only the directed edge. So that's going to be the final one. Okay. So mags are already an equivalence class because we are combining all these ADMGs. So a lot of ADMGs, they are represented by the same mag, some of them, not all in the Markov equivalence class, but many ADMGs are represented by the same mag. So we can use this representation. So I could ask you, what are the ADMGs represented by this mag? And
the graph itself is always one, right? Just the mag itself can be seen as an ADMG just without any conditional.
Yeah, you have to be careful when you say the words, but it is. If you use the same representation, you need to be careful with the bidirected edge, because a bidirected edge in a mag, it's not a latent confounding, but it represents, it can be represented by a latent confounding in an ADMG, right? And that's called canonical mag. Actually, I'm going to show in one example here. So basically, if I give you a mag and I start asking you what are the possible A, D, and Gs that are going to be transformed into this mag, you can basically start listing following from the definition. Yeah, we have to go here. Yeah. No. So you need to follow from here. So to be an inducing path, you need a complete a path where all variables in the middle are a collider, and you have one there. So V1, V2, V4, V5, and V3. So, but the other condition. V1, V2, and V3. So that's directed path here. If this is an inducing path or not. No. So the definition of inducing path is the collider path. So this is not a collider path. V1, V2, and V3. This is not a collider path because V2 in this path is not a collider. So you would have to find an inducing path between V1 and V3. And you are right that there exists a collider path between V1 and V3. But the second condition for this path being an inducing path is that the colliders are all ancestors of V3 or V1. And this happens with V2 but doesn't happen with V4.
But it isn't even a collider path because V5 doesn't function as a collider on that path, right? If you go V1, V2, V4, V5, V3, V5 isn't even a collider.
That's true. Yeah, it's also not. Actually, yeah, you're totally correct because we condition on V5 to make V1 and V3. So a consequence of an inducing path is that you cannot find a separating set for this pair. And we saw before that V1 is separated from V3 given V2 and V5. So conditioning on V5, it's a non-collider. So it's blocking this. So it's not.
But if there were a bidirectional edge additionally from V2 to V3, then, I mean, it'd be trivially, I mean, what would that even?
Yeah, so in this case, no, I think in this case it's not separable, right? So you want.
It'd be the same thing as V5, V4, V2, basically. We just clone that. You'd have V1 directed path to V2, directed path to V3, and then a bidirectional between V2 and V3.
Like this? Yeah, that's the simplest inducing. Not the simplest, but yes. That's the inducing path.
From V1 to V3. Yeah. Okay, so you have the collider path over the bidirectional edge, and then it's the descendant, or it's an ancestor of V3, and so.
Right. But if you have this, V4, V5, and let's make this bidirected. This can be. So if you be conditioned on so this directed edge here makes yeah, we need so this is a collider but it's not descendant of anything, so maybe we can do this. Right, so if I want to separate V1 and V3, then that is this. So I need to condition on V2 because that is this directed path. But then I open this. When I open this, this collider here, right? So I open this collider here. This path, since this is a non-collider, V4 is a non-collider in V2, V4, V5. Then this is open. This entire thing is open. So we need again to block the path. So if we add V4, we open out this thing, and
we would have to add V5, but if
So that's open, and this is, yeah, that's, you see, that's a descendant of this collider. So this collider is open again. So it doesn't matter if we are conditioning on V5 or not. So this is again not blockable. So whenever we have a, I don't know if you were all seeing here, but every time that we have a collider path and every variable is a descendant of either V1 or V3, it's not blockable. So this was an example. So if we had a bidirected edge between V4 and V5 there, it would sufficient to create an inducing path between V1 and V3. Because, so you start, for example, conditioning on V2, and then you see that you need to condition on V4, and V4 is a descendant of the new collider now. V5 is a new collider because we added this bidirected edge, and we are opening this collider. So we cannot block this path because we have to condition on V4. Otherwise, this other path is going to be open. So we form an inducing path.
And then in the mag, we would have V1 as an ancestor of V3 as a direct ancestor. So just adjacent.
They will be adjacent, but also we need to follow the directed path. So V1 would be a directed, that is the directed path. So V1 would be pointing to V3.
Yes.
And you would never have a case where you have both because we form a cycle. So we always have just one path in one direction. Okay. So I want to just list, let's start with this mag here and start listing the ADMGs. So this is the original ADMG where we started. I want you to see how can we could be able to construct, do the reverse process from the mag recover the original ADMG. So basically it's from the definition, right? So from every edge in the mag, we have now the possibility of creating an inducing path to create this edge. Could be just an edge, simplest inducing path ever, but could be like a complicated one. So between V1, V2, and V5, we actually created this inducing path. And I can create other inducing paths as long as I still preserve the ancestralities, right, like this. So I can replace a directed edge as a bidirected edge as long as the ancestralities is still represented here. So you can basically play with the definition and start constructing. So another one is the canonical ADMG, as you said. So basically put exactly the same edge there you put here. But in the case, if you had a bidirected edge in the mag, you would convert as a bidirected edge in a dashed bidirected edge in the ADMG. But you can construct other stuff, right? So for example, this. So I put some notes here. It's exactly what I said. So no inducing path has been created here. So I'm kind of just connecting variables with edges and just replacing this. So it's kind of easy. But what would happen if I do like this? You cannot, right? You said no. Why? You have to always try to recover the mag from this, right? So if you start applying the process of a mag, what would fail in this case? You need to start with the difference. So it's not here, it's not here, it's not here, it's not here. It's here, right? It's the only difference is around here. So what's happening here between V4, V5, and V3? Exactly. Can all of you see this? So that's a bidirected path where this is also an ancestor. So there's no way to separate V4 and V3. So in the mag, I would have an edge between V4 and V3, and I don't have there. So I can put the bidirected edges, but you have to be careful to not create inducing paths like this. So this is wrong, right? Oh no, I touched something. So you can see that they are going to always have the same set of implied condition dependencies because they started from. So the goal of a mag is to be a representation that encodes exactly the same condition dependencies as an ADMG. So all the ADMGs derived from a mag are of course going to have the same condition dependence from the original one that we started with, right? And that's why they already started representing an equivalence class. It's not the whole thing. So that's why implying the same set of condition dependencies is a required, is a necessary condition, but it's not sufficient to belong to the same mag. What is actually a representation that shows just, if I consider just the condition dependencies would be part of the same class? Which object represents only the model, all the models that encode the same condition dependencies? Do you remember? So it's not a mag, it's a class of mags. What is the object? It's a peg. So if I ask you how can we determine all ADMGs that share the same condition dependencies, if I just start by listing those that are represented by the same mag, it's just a subset. It's not all of them, because all of them can be part of other mags, but part of the same peg, right? So there is this theorem that says that two mags are Markov equivalent, so we can move to other mags now to start listing other ADMGs that are part of the same peg or Markov equivalence class. So there is this theorem, I don't know if you remember, that says about the colliders with order, right? So two mags are going to be Markov equivalent or imply the same condition dependence if and only if they have the same skeleton and the colliders with order. So in our example, we have two colliders with order. We don't have here a collider with higher order. Actually, we have, so let's start with the order 0. Order 0 are the unshielded colliders, right? So V1, V2, and V4, V1, V2, and V5 are both unshielded colliders because they are a triplet that's not that's unshielded, like the first and the third variables are not adjacent, so they form a collider of order 0. But higher orders could be created by discriminating paths. Discriminating path is a path that it's discriminating the second to the last variable. So it's a collider path again, but the second to the last is determined by the fact if the implied condition dependencies is given the variable or not. So for example, V1, V2, and V3 is so V1 is separated from V3 given V2 and V5 in this case. And this is a discriminating path for V5. But it's discriminating the fact that V5 is a non-collider. So I have to be careful on not creating any collider with order in any other mag. So I have to be careful to keep these two colliders of order 0 and not creating any other collider, maybe with other higher, even with other orders. So for example, I cannot create a mag where V2 is going to be a collider in V1, V2, and V3. This would create a collider with order 0. Or I cannot create a collider in V5. That's what we discussed in the previous slide. If I create a collider here, then it would be a collider with order, so it would be part of another mag. And Markov equivalent mags are those that share the same colliders with order. So if I have another mag that has another collider here, is not part of the same Markov equivalence class. Okay? So we need also to pay attention on making sure that we are creating valid mags. So what are the three conditions for mags? Can you remember? The first one is there is no cycles. The second one is no almost cycles. And the third one, you won't use it. I will never, I guess, cover the case of undirected edges. But that is this case. If you have undirected edges, you cannot have arrowheads pointing into undirected edges. So you have a selection bias. Maybe I should start covering now. So if you have undirected edge, you cannot have like a spouse or a parent of a node that is part of an undirected edge. That's the third condition. But let's keep it simple. So if, for example, I start applying this criteria to create different mags that are Markov equivalent to the first one there. So what I need to do is just make sure that I'm not creating any colliders with order. So keeping just this as the set of colliders with order. It has to be the same set, and I cannot violate the conditions of PMAG. Oops, I'm very here. So in the first one, I just changed from V5 to V4, and now it's V4 to V5. So it's in red there. So you see that's not creating colliders, it's still fine. So I also can change the V1 and V2 here because it's not creating colliders, so the collider is still there. I can add like V1 as a bidirected edge, so I'm not forming any collider. Also, this thing here is not violating anything regarding, I'm not creating a cycle and an almost cycle. So this is a directed edge, but it's not forming a almost cycle, right? So what would happen if I use this and just flip the V5 and V2 as a bidirected edge? Oh, sorry, V2 and V4 as a bidirected edge. You cannot do it. It's an almost cycle. So I cannot have a mag where this is a bidirected edge. Although it's not creating any other colliders that it shouldn't, it's violating the conditions of being mag, right? This is also fine. You see, it's creating a bidirected edge here. Also, I'm keeping these directions. If it was the other direction, this would create an almost cycle. I mean, you can just get many variations as long as you're not creating colliders on V5 here, or in this triplet, or in this other triplet. Anyways, you have several variations. You need to pay attention on not just violating the conditions of mags. So you can kind of list from this, you can apply the theorem and easily just get different mags, right?
And almost cycles only if there's one bidirected edge on half of the cycle?
No, it's yes, only one. So it's creating the cycle, but then the last one cannot be complete cycle, so it cannot close the cycle. It cannot be just a bidirected edge. Okay, there's many. So yeah, you can try at home. Yes. This? So this collider here, it's fine because it's not collider with order. It's so
it's shielded because V2 and V4 and
yeah, and there's no discriminating path of higher orders here. So maybe it's a bit hard to see in the beginning where are the colliders with order, but like keep it simple. Like if I ask you, like just give a few variations, just create the simplest ones, right? So just make sure that you're not creating colliders of order 0. So you keep the same colliders of order 0. This is clearly would be a collider of order 1, so you have to be careful to not create collider here. But this is not being discriminated, so this is also cannot be discriminated. Anyways, you need to find what would be the colliders with order in each of them to see if the same sets, if they are in the same sets.
Just as an example, if we had a bidirect edge between V2 and V5 and a bidirect edge between V5 and V3, would that also be a map?
V5 and V3?
Yeah, and V2 and V5.
No, because then
Bidirected here and bidirected here?
Then you would have all of it, then you would have a circle.
No. Bidirected here and here,
Yes.
together. So you would have the collider. This would be the problem. But we are not forming a cycle. A cycle would be if this was directed, and bidirected. You need to
compared to the original one.
Yeah, so just moving V5 to V3 as a bidirected, you cannot. So you see here there's no example like this. You can have more. No, you cannot have it. That is, you can never create a bidirected here, and we are going to see why later. Can you see already why? You cannot have just the bidirected in V5 and V3. It's not automatically, but yes. If you put the bidirected edge here, then you cannot form this cycle. You cannot have a collider. So this V5 has to be pointing to V4. And when V4, and then you could have a bidirected edge there. You form some cycle. So let's start V5 and V3. I want this. This is going to violate something. So the first thing is that I cannot have a collider. I cannot have a collider here. So let's put the V2. So this for sure has to be like this, and this for sure has to be like this. Because this is a collider of orders 1, and this one here would be a collider of order 0, right? So I cannot create them. So the V1 is so this is a collider. So you know the V1, V4, and V2 forms a collider. So you need this. You cannot remove this, but you don't know what's happening here. And
you can't create a cycle there, so it has to be bidirected.
why you cannot just do this? So this is not a cycle.
Yes, but I meant between V2 and V3. You need the bidirected edge, right?
If I do this, is a cycle.
Yes.
If I do this, I block. I create a collider here, and I cannot. So you cannot do this. And if I cannot do this, why I cannot have like this? I can. Is this valid or not?
No, because of V5, V2, V3,
V5,
right?
V2, yes. So you cannot. Yeah, good. Because you cannot have this. You'll see later. So that's my questions. We already tried, but I would like you to try to construct mags where you change these two edges. So we just saw that we cannot do this, and we also saw why we cannot do this, right? So you cannot change. So a easier, in my opinion, way of listing these modules is through the peg. So instead of applying these colliders of order, if I ask you the question, like let's start adding listing modules that are Markov equivalent to one ADMG, you can just get the condition independencies implied by the model and run the FCI. So the FCI over the conditioning set, the list of minimal conditioning sets could be our start. So how we do it? So this is just for reference. So we have the DMG there, the MAG there. If you apply the separation and M separation here, you see the same sets there. So how we construct the pack? So we start with the complete pack, a complete graph, right? And what's the next step?
Remove the edges that are not necessary because of conditional independency.
Right. So which edges are there? Oops, it's fine. V1 and V3, V3 and V4, V1 and V5, and V1 and V4. Right. So it's just remove it. What's the next step?
Next, we add the colliders.
Perfect. Perfect. So the rule 0 is like just get the triplets that are unshielded and see if the separating set includes or not the variable in the middle. So in our set, we have V1 and V5 being the empty set, they are separated by the empty set. So that is this triplet is unshielded. What about V2 then? It's not part of the separating set, so sure, exactly. What about V1 and V4? So V1 and V4 forms this unshielded triplet, and V2 is not part of the separating set. So we are going to have this and this. Okay. What are the next? So we have now this stage. We need to start applying the rules. Can any of you give me one rule that can be applicable here?
I think V2 to V3 has to be a directed edge to V3.
V1 to V3?
Yes, because of rule. Or it has to go into V3 at least.
Sorry, you're saying V2 pointing to V3.
Yes.
What about here? Nothing? It's just the arrowhead?
No, that has to be something to it. I think it's a different rule.
It's a directed edge? No? It's a bidirected edge? Directed from V2 to V3? Yes. It's a rule 1. The rule 1 is the most important one. You need to at least this one to know. That is basically, so it's here, the rule 1. So you find an unshielded triplet that was not a collider before, so it has to be non-collider. It's very simple. So you show that this is a directed edge from V2 to V3. It's the only possible way. Why cannot be undirected?
Because otherwise it would create a collider between V3 and V4.
No, undirected. Why this is not an undirected edge?
Oh.
Is it still a non-collider here? But why cannot be undirected? Is the third condition of mags. So undirected edges cannot have arrowheads pointing inwards. So that's why you also have arrowhead here. So it has a tail to not form a collider, and also has the arrowhead because you cannot violate the third condition of mags. Okay. So that's the most important one. You'll see later also another thing related to it. But you find a cause, and it's a definitive. We call it definite cause. We're going to see hopefully in the end of this thing. I'm going to give you a new definition. So now we are here. Now, can anyone give me another rule?
Is it rule 2 that there has to be an arrow pointing into from V5 to V3? Because I think
the rule 2 would be if this was not oriented. No, it's even different. You need a collider here. Yes, sir.
Rule it was, but we can't create cycles, so we have to create a directed edge between V5 and V3.
So for next week, I will require you to remember the rules from 0 to 4, and the rule that we have applied here is the hardest one, which is the 4, and it's about applying discriminating path. So we need to find a discriminating path here. Can anyone see a discriminating path for us to apply that rule? So basically, if there is a discriminating path and the variable is part of the separating set, then it's we're going to orient x pointing to y there, because it's definitely non-collider. And to know if we apply or not, we are going to use this condition independence. So I'm giving you even the pair that has a discriminating path between them. So starting from V1 to V3, we need to find a collider path.
V1, V2, V4, V5, V3. No, there's no
V1, V2, V5, V3.
V1, V2, V5, V3. Yes. And what happened with V5? So if it's part of the separating set, which edge will you change here? So we are going to move this. So it's another edge that we know for sure that's from V5 to V3. So from the mags, we were listing them. You remember, this was an invariance we couldn't change. This is another invariance that we couldn't change, right? So a mag, actually, that's our final peg. So if you apply then the separation, M separation for mags, M separation for pegs, you check. Those are the condition dependencies implied by all of them. What are the learned invariances here in terms of ancestor relationships? So we have, for example, V2 is a non-ancestor, or is definitely not ancestor of everything that's pointing to it, right? So V1, V5, V4. On the other hand, V2 is an ancestor of V3. Also, V5 is ancestor of V3. We have these definitions of definite status triplets in a peg. Can any of you give me?
I have a question. Would we also know that V4 and V1 are ancestors of V3?
No. V1 is not ancestor of V3. It's a possible ancestor of V3.
Okay.
You can have a bidirected edge there, right? If you have a bidirected edge between V1 and V2, go back here.
But how would that change how we feel about V3?
Like this here.
But wouldn't V1 still be an ancestor of V3?
Do you think it is here? To be ancestor, you need a directed path from V1 to V3.
Well, then it isn't.
No. That's a. Why you're looking? I'm not late, right? Yes, almost. You're angry at me.
No.
So you can change. That's why it's not an invariance. So that's why in the peg. So if we start from so if I ask modules inside of a mag, so now I'm forcing V1 has to be ancestor of V3. So inside of one mag, all this V1 to V2 have to be ancestors. So V1 has to be ancestor of V2 because this is forced. So it's encoded in one mag. But you have different mags now that are equivalent to each other in the sense that they imply the same condition dependencies. So I'm no longer asking you to preserve the ancestor relationships of one module. I just want to represent condition independencies. And in this case, I can create many mags. And because of this class of mags, which will form a peg, we will have things that are not necessarily invariant. So that's a case where I can construct something where it's not ancestor. And in a peg, this is going to be represented by this circle, right? So we have a circle there. So I think it's going to clarify later. So in a peg, what is invariant? So if now I give you a peg and I start asking, let's list the models from a peg, you have to preserve the invariances. So the invariances are not only the invariances in terms of ancestralities, but also the definite status triplets. So for example, all the colliders, they have to be preserved. If I said that this is an arrowhead in a peg, it's because all models in this peg have the same arrowheads. So I cannot change this arrowhead. It's the same for definite non-colliders. So V5, it's a definite non-collider in the triplet V2, V5, and V3, and in the triplet V4, V5, and V3, because of the tail out of the V5. So I can never create a collider in these two triplets, as we saw in those examples as well. It's going to create some problems if you start to understand what's happening. But if I give you a peg, you don't even need to understand what's going on. You just need to preserve what's there, which is in terms of ancestor relationships and this definite status triplets. So for example, so we have to pay attention to a few things. So we cannot create like pegs that are going to generate invalid mags or things that are not valid. We cannot add more inducing paths than we should. Anyways, those things that we discussed before, but all invariances, including ancestralities and definite triplets, have to be represented. So list of mags. So I have to convert the circles into whatever I want, as long as I'm not creating violations. So for example, I can put a tail on V1. I can put a tail on V5 from V5 and V2, and V4 to V2 can be a tail as well, and then I can decide which direction I have here between V5 and V4, as long as I'm not creating a cycle or something like this, or almost a cycle, right? So if this is a valid mag, then I can create ADMGs following a mag as we did before. So for every edge in the mag, I can create either an edge or an inducing path. So in this case, I'm just creating something very simple. So I'm keeping the same skeleton and adding a few bidirected edges that's not inducing any, creating any inducing path. I can create something more complex like this one. So in this case, I don't have an edge between V2 and V5, but that's fine because that is an inducing path from V5 to V2 through V4, right? So I have to create an inducing path for every edge in the mag, and I have to respect the orientation. So V5 has to be pointing to V2 through a directed path. So V5 it has to point to V4 and has to point to V5 to V2. V5 to V4 to V2, because I cut the ancestrality here. So to make V5 the ancestor of V3 and ancestor of V2, this has to be the same direction. So you need to follow and make sure that you are representing the same models. So I'm just listing here, that's another example. So there's two bidirected edges, it's not creating an almost cycle. Now I decided to put a bidirected edge between V2 and V1 and V2. So in this case, is the edge between V1 and V2 is only bidirected because V1 cannot be ancestor of V2 and V2 cannot be ancestor of V1. So the only possibility is bidirected edge. So this again, bidirected edge, so only bidirected edge. Same for V4 and V5. The directed edge from V4 to V2 can be confounded as this one. Anyways, it's just making sure that it's everything is valid. That's another example. So I'm always considering cases in the second column here where I have an inducing path. So for example, I have an inducing path in this case that, so for the edge between V2 and V5, you see that V2 is not ancestor of V5 and V5 is not ancestor of V2. And this is represented by this inducing path. And you know that V5 is not ancestor of V2 and V2 is not ancestor of V5. So that's the only inducing path that I can construct to preserve these non-ancestralities and also create the edge here. Now, in these other cases, it's different, right? Because V4 is ancestor of V5. So the edge now is here in this side. So I still have an inducing path, but I'm representing the ancestrality from V4 to V5 here. Okay? So you need to be careful with the edges, the ancestralities, and the validity of the mags when you're constructing these models. I want to give you just this definition because I think it's falling exactly in the category of the examples that we are having here. I won't ask you anything complicated for you, but an edge, that is this definition that's called visibility. So in a mag or in a peg, a directed edge, so the fact that I have a directed edge in a mag or in a peg doesn't mean that this edge is a directed edge in the underlying module. We saw examples like this. We are going to see again the same examples. So the fact that I have an edge between X and Y, where it starts with an X, with a tail on X and an arrowhead on Y, this doesn't mean that it's not confounded. So we have this concept of visibility that it's going to satisfy the concept if there is a node. Let's just put the example here. So if there is a node that's pointing to a variable, and this node is not adjacent to the other variable. So let's consider this directed edge from x1 to x2. It's directed in a peg. To know something that we call it visibility, so the visibility of this edge, we need to find another variable that's not adjacent to this variable here. So it's a directed edge, so from x1 to x2. So cannot be adjacent to x2, but has to be not only adjacent to x1, but with an arrowhead into x1. Is exactly the rule 1 that's being applicable here. Because if that's the case, this means that I cannot have a bidirected edge between x1 and x2. So we cannot have this edge confounded. And it's much more than that. You cannot create an inducing path to replace this edge when you construct a model. So it's definitely a directed path, unconfounded. You have no confounding between them. So this is the simplest case. There is the other case that's there, that it's a collider path. That's another example. So we are going to use this letter V just to represent. So there are two visible edges in my example, this one and this one, because it's the same application for the variable V. We also have this other case. It's a bit more complicated, but it's a case where we have a collider path, and the last variable here has to be pointing with an arrowhead. So this will be visible, this is visible, but that one is not going to be visible. So we need an arrowhead to be on the variable. That's very important. If you don't have it, then this is not visible. So in this case, these two variables, these two edges are going to be visible. So in my example, so going back to the example, the edge between V2 and V3 is visible. Why? Well, because of V1. What about the edge between V5 and V3? Is visible or not? There's no arrowhead pointing on it. It eliminates all the two conditions, so it's not visible. Which means that I can create models where there's no directed edge between V5 and V3, only a bidirected edge, or both. The point, so that's two cases here. So I can never have a bidirected edge here. if you try, you're going to violate several conditions, like the fact that this is a non-collider. But you can create here an example that's confounded. So you have bidirected edge between V5 and V3. So this is confounded. This is also confounded. It's not even directly connected. It's still ancestor. So it's respecting the ancestrality. But there is a confounding that you cannot block. You cannot remove it. So if you try, so just the case of V2 and V3, this means that it can never be confounded in a causal diagram in this equivalence class. You can try at home. You won't be able. You have to show some contradiction. I still have a few minutes. So I want to touch on a topic that's ongoing research. So, but it's again, it's really related to what we are discussing, and helps you to kind of understanding the limitations, why we still have this issue in the theory, which is about incorporating background knowledge. So suppose that I have this pack, as we learned now, and I tell you that V4 is actually a cause of V5. Okay. So what we can do? Oh, now great. Now I have an arrowhead pointing V5. This arrowhead is so V4 is not adjacent to V3. So this kind of creates visibility for the edge between V5 and V3. That's great. So now you can never construct a model that has a bidirected edge between. So it's reducing the size of my equivalence class because I have to satisfy this new condition. So one attempt could be apply the rules of the FCI again, because now I can construct new triplets. So in this case, I won't have any orientation, so I'm going to give you another example so you can see the issue. But you can, of course, create or reduce the size of the equivalence class by adding this. But the way that we, so an algorithm that can update the model in a complete way, in the sense that I do the best that I can do after incorporating the background knowledge, this is still unknown. We have a few cases where we know how to do it, but in the complete sense, we don't know an algorithm to do this yet. So here, we can do by hand, of course. We can take example by example and do by hand. You can do this. But an algorithm that does this in an automatic way and it's complete, this doesn't exist. So in this case, we stop here. We cannot apply any other FCI rule. We just got the visibility of the edge, and that's it. Yeah, this is an exercise you won't be able to do it. So this is another example, and I have a warning. Why this is complicated? Because pegs represent Markov equivalence classes, and the definition of a Markov equivalence class is a class such that all the modules they encode the same set of condition dependence. Period. I'm not saying anything more. So any knowledge that you bring that's not from data, it cannot fit to the definition of Markov equivalence class. It's going to be a new equivalence class, but not the Markov equivalence class. So everything that we learned, for example, definite status triplets, you cannot apply anymore if you have background knowledge. Algorithms for identification that we are going to see later, they won't apply if you created a new class by incorporating knowledge. You need to develop a new algorithm to account for this. So everything that we know for, so what I covered in the lecture and most of the algorithms that they are dealing with pegs don't allow you to incorporate background knowledge. This is so there is no complete algorithm that allows you to do causal discovery with background knowledge. So this is an example. Suppose that this is a peg. Okay. Oh, sorry, that's my graph. Original could be anything. Could be a meg or could be a ADMG. Let's suppose that's an ADMG. But that's my peg. That's my output of the FCI. So you couldn't learn much. It's just there's no edge between B and Y. And then I tell you, oh, from background knowledge, I know that B causes A. Okay, great. Now what can you do? Can any of you know which rule I could apply? To X? From here to here? Which rule? No, one. The one needs that this variable is independent of, separated from this. So maybe this. Yeah, right. So it's a triplet, has to be unshielded to apply the rule one. So you can apply the rule one, but for this edge. So from rule one, you have this. What about now? That's not unshielded. So you stop here. However, if I try to now list some mags from this, I do this. Oh, okay, let's create like I can do whatever I can do here. I put an arrowhead here. I can do it. I'm not creating any. So this is a definite no collider. So I do like this. Actually, if once you put the arrowhead here, you can apply the rule one again and do the same. You can find this has to be done. But what happened now here? A cycle or almost cycle, whatever is here, you violate it. So you cannot do it. So you have to go back. What's the only thing that can happen that you can do? You have to flip. So you can never put an arrowhead here, right? This cannot happen. So is this? Did you see it? So this, oops.
Only if there is one going to XP, right?
So this is known. Okay, you use the knowledge, you use the rules, so this is true. But I could now start listing mags inside of this. And I would try to do some mag that has an arrowhead pointing to X. I want this.
And arrowhead pointing to B, right?
Yeah, so once I put the arrowhead here, automatically I have to put the arrowhead there because I cannot create a collider. So this is for sure, it's a consequence. Once I want to create a model here, this has to be for sure.
Right.
But then I create this cycle or almost cycle. So I cannot have an arrowhead here. If I don't have an arrowhead here, it has to be tail here. And I cannot have another tail here because of the violation of mag. So it has to be this. So this would be the complete equivalence class under background knowledge, but we don't have an algorithm to do. But you can do by hand. So it's important for you to know. So if you have background knowledge, you can kind of play with the object and see whatever. It's really complicated in a large scale, but in a small example like this, you can do it. But I could ask you, for example, give me a model inside of the equivalence class such that B is a cause of A. And then you would have to go through this process. One way to do it is, I mean, you can draft by hand until you get it done. But one easy thing to do is to get the mag, update the peg, and then get any model that's compatible with this. That would be the easiest route to get the answer. So the tools that I showed here help you to do a lot of things from the point of view of getting only condition independence from data and recovering the causal models, right, from it. So that's it. Don't forget, we have the test exam next week, and I listed here some of the topics that I believe they are important for you to learn. So several of them I considered kind of easy, and then I didn't cover here, but you can go back to the lectures and see it, like structure causal models in the version of observational case, interventional case, factorization according to the extended parents, projection is something that maybe helps. For example, in all these examples that I explained to you, maybe you could consider remove the variable v4. You see that everything would be easier. And then you worked with the projection, and then you trivially would satisfy, you would get, for example, the fact that V2 is a cause of V3, V5 is an ancestor of V3 without using V4. So working with projections are really useful in Prezi. Yeah, everything is here. Markov equivalence classes and mags and pegs I just explained. So I think if you know this, you are going to be very well in the test, and we will be prepared for the next stage of our course. All right.